So far we've looked at functions of one variable, like y equals f of x. Now we're going to look at functions of more than one variable. For example, if we have z is equal to f of x and y, that's a function of two variables. Or if I said w is equal to f of x, y and z, that would be a function of three variables. An example of a function of two variables might be elevation. So if you had a map and you have your x and y coordinates on the map, or latitude and longitude or whatever, elevation of the ground at a particular point on the map could be considered as a function of those x and y coordinates. So in that case, z would be the height or the altitude or the elevation, and x and y would be your x and y coordinates or your latitude and longitude. An example of a function of three dimensions might be the temperature in a room, the air temperature. If you had a room with various sources of heat inside it, the air temperature would vary depending on where in the space you were. If you had your x and y coordinates laid out on the floor, like this, if that was flat on the floor and you put your z coordinate up the wall, then a position inside the room could be given by your x, y and z coordinates. So if you had some point in space inside the room, you could project it down onto the floor and then over to each wall to get your x and y coordinates. Let's call it y1, x1. And you could project it in the z direction too. This height up here, that would be the z coordinate. We could say project it into that wall and then along that wall there to get your z coordinate. So the x coordinate would be, say, the distance from one wall in the room, the y coordinate would be the distance from the other wall, and the z coordinate would be the height above the ground. So in that way you put your three coordinates together to specify a point in the three-dimensional space within the room. And then if you wanted to express the temperature, for example, as a function of where in the room you are, that would be a function of three variables, your x, y and z coordinate. The volume of a cylinder, for example, is equal to pi r squared h, if that's r and that's h. So you might say, if we were looking at a problem where we had a cylinder where the radius and the height were both variables, I might consider the volume to be a function of r and h, the radius and the height, or a function of two variables. So if I supply a value for r and a value for h, that function will give me the value for the volume. Similar to how in the temperature of a room example, I would supply x, y and z coordinates for the point in the room, and I would have a function that would take those three coordinates and tell me what the temperature was at that point. So how do we differentiate a function of more than one variable? Well, what we can do is differentiate with respect to one variable while treating all the other variables as constants. For example, if I have z is equal to f of x and y, then the two partial derivatives that I could take would be del z del x or del z del y. So I've introduced a new notation there, which is this thing, del. It's like a D but without the bit at the end. You draw it like this. So the partial derivative is denoted with del. So z is a function of x and y. I can take del z del x or I can take del z del y. That's the partial derivative with respect to either x or y. So let's say that z is equal to f of x and y, and in particular it's equal to x squared plus 3xy plus 2y cubed. Now the partial derivative of z with respect to x will be the derivative of that function entirely with respect to x, treating y as a constant. So this is not like doing implicit differentiation. Before, when we had x's and y's in the same expression, y was implicitly a function of x. Here, y is another independent variable. And since we're doing a partial derivative with respect to x, we're going to treat y as a constant. So the partial derivative of z with respect to x here will be 2x, simple enough, Now I have 3xy here. In this case, y is treated like a constant. So the derivative with respect to x is just going to be 3y. Because I had 3y times x, and the derivative of some constant with respect to x, it just leaves you with that constant. And finally, the derivative of 2y cubed with respect to x is 0. So it's just 2x plus 3y. The other partial derivative that I could take would be with respect to y. Del z del y. So the partial derivative of x squared with respect to y, remember now I'm treating x as the constant and y is the variable. So x squared just becomes 0. 3xy becomes 3x. And 2y cubed, well, that 2 stays in front, and what the derivative of y cubed with respect to y is 3y squared. So I end up with 3x plus 6y squared. I can also take a second derivative. So let's look for del 2z del x squared. So to get that, I just differentiate del z del x again. So I'll write that down explicitly. So I'll do a partial derivative with respect to x of del z del x in order to get that second partial derivative with respect to x. So I'll put that in explicitly again. I'm going to differentiate partially with respect to x, 2x plus 3y. And that's going to give me just 2. So 2x becomes 2, and 3y differentiated partially with respect to x is just 0, because I'm treating y as a constant. Let's get the second partial derivative with respect to y. So that's the derivative with respect to y of del z del y. So I do a partial derivative with respect to y of 3x plus 6y squared. That 3x differentiated with respect to y is a 0, and 6y squared becomes 12y. So I end up with 12y. Now there are two more partial derivatives that I can take, and that's if I go first with respect to x and then with respect to y, or vice versa. So that's what you call a mixed partial derivative. So I'll write that down next. So we can take a mixed partial second derivative, del 2z del x del y. So that is where I would first differentiate with respect to y, and then with respect to x afterwards. So that's the partial derivative with respect to x of my partial derivative with respect to y, which was 3x plus 6y squared. So I differentiate that with respect to x, and I just get 3. 3x becomes 3, and the 6y squared goes to 0. If I do it the other way around, I'm actually guaranteed to get the same answer always. Let's say I go del y del x. That's equal to the partial derivative with respect to y of del z del x. So that's the partial derivative with respect to y. We got del z del x earlier. It's 2x plus 3y. So now I differentiate that with respect to y, treating x as a constant. So 2x differentiated with respect to y is 0, and 3y is 3. So I get 3, the same answer. And in fact, it's a theorem. It's always true that the second derivative, the mixed partial second derivative I should say, is the same no matter which way around you do it. Here's another example. Here I have z again, a function of x and y, where it's equal to x times e to the power of xy squared. And I'm going to find all of the first and second partial derivatives. The first one we'll find is del z del x, partial derivative of z with respect to x. So we treat y as a constant here and we differentiate with respect to x. So we will need the product rule first. So that's equal to x times the derivative of e to the power of xy squared plus the derivative of x times e to the power of xy squared. So that's a product rule, where I said u equals x and v equals xy squared. And remember that we're treating y as just like any constant. Right, so that x stays as it is now, and we differentiate e to the power of xy squared with respect to x. This is a chain rule type thing. Remember that e to the power of x, when we differentiate it, gives us back e to the power of x. It doesn't change. So if we differentiate with respect to everything up top there, and then we multiply by the derivative of what's up top, by the chain rule. So what we get is y squared times e to the power of xy squared. If I differentiate x with respect to x, I get 1, so that's just 1, times e to the power of xy squared. So let's write it down again. We get x y squared times e to the power of xy squared plus e to the power of xy squared. If I want, I could factorize that and say it's equal to e to the power of xy squared times xy squared plus 1. Either way is fine. Next, I'll get the partial derivative with respect to y. So now I'll treat x like any other number, like a constant, and I'll differentiate with respect to y as a variable. So that x in the front is going to stay as it is. We're multiplying by x, so now that's just a number. So the derivative of xy squared with respect to y is 2xy. So the e to the power of xy squared stays as it is, but what happens is that by the chain rule in front of it, I get the derivative of what was up top there, which with respect to y, in this case, I'm treating x as a constant, that 2 comes down and I get 2xy. So putting that together, it's 2x squared y times e to the power of xy squared. What about second derivatives? The second derivative of z with respect to x. Well, all I do is I go again with respect to x and del z del x. So that's equal to the derivative with respect to x of e to the power of xy squared times xy squared plus 1. So I need a product rule for this, where u is e to the power of xy squared and v is xy squared plus 1. So what I'll get is e to the power of xy squared times the derivative of xy squared plus 1 plus the derivative of e to the power of xy squared times xy squared plus 1. Product rule. So that's e to the power of xy squared. The derivative of xy squared plus 1 with respect to x is just y squared. Because that y squared is treated like a constant because we're differentiating with respect to x, and that 1 goes to 0. Plus the derivative with respect to x of e to the power of xy squared. Well, that y squared comes down in front, and we get times e to the power of xy squared by the chain rule. And that xy squared plus 1 stays as is in front. So I have y squared times the xy squared, xy to the power of 4 times e to the power of xy squared plus y squared e to the power of xy squared. That's multiplying out that term on the right. Now finally I can factorize what I can out of this. So I have a y squared times e to the power of xy squared everywhere in there. So what I can do is I can bring that out in front, and then inside the brackets I get 1 plus x y squared plus 1 actually. So that's actually equal to y squared times e to the power of xy squared times xy squared plus 2. That's that. What about the second partial derivative with respect to y? The second partial derivative with respect to y, we just differentiate with respect to y again, the first derivative. So that first derivative was 2x squared y e to the power of xy squared. So get the partial derivative of that expression with respect to y. That means I'm treating x as a constant. So I'm going to do product rule. So u will be 2x squared y and v will be e to the power of xy squared. So I'll have 2x squared y times the derivative with respect to y of e to the power of xy squared plus the partial derivative with respect to y of 2x squared y times e to the power of xy squared. So that 2x squared y is still here. The partial derivative with respect to y of e to the power of xy squared, we've done that already. So the derivative of what's on top with respect to y is 2xy. And then by the chain rule, that is the derivative. The derivative of 2x squared y with respect to y is 2x squared. So I multiply all that out. I have 4x cubed y squared e to the power of xy squared plus 2x squared e to the power of xy squared. And I can factorize that if I want to, because I have 2x squared e to the power of xy squared in both terms. So I can factorize that out and I get 2xy squared plus 1. And that is the second partial derivative with respect to y. So there's one last one we want to get. I want the mixed derivative. Remember that they're both the same, no matter what order I do them in. So the thing to do is to have a look and see which one looks easier to do. To me, it looks easier to get the derivative with respect to x of del z del y. So that is the derivative with respect to x of 2x squared y e to the power of xy squared. This is a bit like the last one we just did, except last time we went with respect to y and now it's with respect to x. So again, I'll do a product rule and I'll get 2x squared y times the partial with respect to x times e to the power of xy squared plus the partial with respect to x of 2x squared y times e to the power of xy squared. Remember, this time we're differentiating with respect to x and treating y as a constant. So I get 2x squared y here, and the derivative of what's on top there now in the exponent with respect to x is y squared. So by the chain rule I get this. The derivative of 2x squared y with respect to x is 4xy. So overall I have 2x squared y cubed times e to the power of xy squared plus 4xy times e to the power of xy squared. And again, that's something that I can factorize. I have 2xy e to the xy squared in both sides. 2xy e to the power of xy squared. So when I take that out, I have xy squared here, and I have 2 over here. And that is the mixed second partial derivative. So we should be basically done here, but what I will do, one last thing, is just check if I do the differentiation the other way and show you that it comes out the same. So there I've done it the other way around, getting the partial derivative with respect to x first, del z del x, and then differentiating afterwards with respect to y. And you see that you get the same answer, and you always will for any function, or at least any of the functions that we're dealing with. Here's an example with 3 variables. Let's say that w is a function of x, y and z, and it's given by x times the sine of y times z. So let's look at the partial derivatives we can get. We can get del w del x. So here we treat x as our variable and differentiate with respect to x, treating y and z as constants. And since we have x times a thing that now just has constants in it, we just get back that thing. So del w del x is sine of y times z. What about del w del y? Well, x now is just a constant, so differentiate x times sine of yz with respect to y. Now x and z are constants and y is our variable. So del w del y is equal to y times the cosine of yz. By the chain rule, it's going to be that times the derivative of what's in the brackets, which with respect to y is just going to be z. Because I had yz in the brackets. If I had 5 times y in the brackets, that would have been 5 outside. But I have z times y, so I get z outside by the chain rule. That's xz cosine yz. What about del w del z? Now z is our variable, and the x and y are treated as constants. So in this case, I get x times cosine of yz times the derivative of what's in the brackets with respect to z, treating y as a constant, which gives me y. So it's xy, it's cosine of yz. Let's try some second partial derivatives. What about the second derivative with respect to x? Well, that would mean taking the partial derivative with respect to x of sine of y times z. Now there are no x's in that, and y or z are treated as constants for this derivative, so that's 0. What about the second derivative with respect to y? Well, I'm going to differentiate with respect to y, treating the others as constants, this thing, x, z, cosine yz. So those x and z are just numbers as far as we're concerned now, just constants. So it's going to be xz. Derivative of cosine is minus sine. And the derivative of what's in the brackets with respect to y is just z. So I get minus xz squared times sine of yz. Let's try a mixed one. Let's try del 2w del x del y. Well, that's equal to the derivative with respect to y, we can do it either way, of del w del x, or vice versa. So that is the derivative with respect to y of sine of yz, which would be equal to cosine of yz times z. What about the other way around? Let's say I did del x of del w del y. Well, then it would be del x of xz cosine yz. Well, now x is the variable and the rest are constants, so I have x times z cos yz, and since z and y are just constants, that just leaves me with z times cosine of yz, which is the same as I had above. So either way you get the same thing. And I could do the other ones. I could do del 2w del z squared, or any combination of x, y's and z's. But I think you get the picture. So that is partial differentiation. There's really nothing to it. It's not any harder than normal differentiation. But for each derivative you take, you just need to remember which is your variable and which are being held constant for that particular differentiation.